Really, the good thing about our collaboration has been that we are using complementary techniques. So he is covering much more the microbiology, quantification of cells is the main specialty, and we work more with geochemical tools where we target microbial compounds that are either part of the cell or that are being released by the cells during metabolism.
How deep life exists and what is the functioning of microbial life and how do they evolve during the history of Earth's change.
What we don't really understand are the limits of life. So we don't know really what the extension is of the deep biospheres. We think that temperature is regulating it, but there could be other factors such as energy or water availability or simply physical factors. Is there enough space? Because the pressure goes up when you go deeper and material gets more and more compacted. Microbes may just not find a very good habitat there anymore.
One of the big challenges in this project was to minimize or avoid the contamination from drill fluid. We want to know the two indigenous microbial signatures from the core samples.
Going into the sock. No, goes in the sack.
There are multiple sources of potential contamination. The probably most drastic one comes from the drilling, where drilling mud is circulated through the borehole, and this contains chemical additives, but also seawater, potentially microbes from the ocean, and they are introduced into small fractures in the drilling core. That's what we want to avoid.
Going into the sock.
We scan cores for potential fractures. So my colleague, co-chief scientist Fumio Inagaki, and I have to make the decision after each core. We scan with an X-ray scanner these cores three-dimensionally. So I'm searching for potential places where drilling fluid can penetrate, and this would be an example where we have a crack, so that is probably happened through drilling, and we have this drilling fluid through the drilling technique, and that can penetrate in here. So if we have this as part of a sample and analyze it for chemistry, then our results will be wrong. So we have to carefully check where we take samples.
I'm quite happy that we have a multidisciplinary expertise team. And We have a geologist, sedimentologist, and physical property. And of course, this expedition is dedicated to microbiology and biochemistry. So we have a great staff of life science.
We have about 30 scientists from different countries and different backgrounds. So it's the best part of my job to combine each other's interests together, and it makes them work into one goal. And I think this cruise has a very good science party team, so they are working very closely with different groups.
Maybe silicate or some other stuff.
And now it's already in the hands of microbiologists.
I'm in charge of monitoring the contamination in the sediment cores during drilling. And we do this by adding a chemical tracer compound to the drilling fluid. And then during the drilling process, this drilling fluid is used to cool the drill, so we don't heat things up too much and destroy the samples. And so when samples are then retrieved back on board, I take samples from the outside of cores and also from the inside of cores, and then measure the chemical tracer concentration in that. And using that, we can then calculate what the contamination is with the drilling fluid. And another thing I do on board is extract DNA from some of these samples. And then together with my colleagues, we are then quantifying the numbers of bacteria and archaea, which are the two main groups of microorganisms that we expect to find here. And we are looking at their numbers and how they change. And this will be combined with other kind of quantitative assays in which we will be able to estimate the cell numbers for different types of microorganisms.
See that, it really looks like coal. This is fantastic.
I'm on board here as a logging specialist, and this is the ocean floor. And then we start drilling at this point and then go deeper, penetrating to further deep. This is 1,000 meters deep from the ocean floor, and then we are now nearly to 2,000 meters deep from the ocean floor. We are now drilling in this interval, which is marked by that black color. And this black color is the primary target of this expedition, because this depth has many reflection seismology feature here, and that indicate there must be many core layers here.
At this point, we just verified yesterday the presence of the coal bed. We only suspected that the coal bed would be here based on seismic evidence, but that's never clear-cut, the interpretation. So now we know it's here, and now we are, in the next 3 weeks, we will find out what it's doing.
My speciality is looking at the organic compounds that you find in rocks. So rock looks like this. I'm interested in this goo that we take out of the rocks. And the thing that I'm doing on the ship is, instead of just looking at this goo as goo, I am trying to analyze specific chemicals or molecules within the rocks that we find here. And the aim of this expedition, one of the key aims, is sort of tracking the point at which something biological changes into something geological. So coal is made from trees. Trees are biological. Trees die and make soil, and then the soil slowly changes into a rock. And as that happens, the chemicals inside change, and they go from living things to being chemical fossils, and I'm studying chemical fossils. The main application would be just to explore and understand what's going on. There's been several appraisals of how much biomass or living organic matter is buried in the sediments in the oceans. And this is a chance to not look at it spatially over a map. This is a chance to look at it with depth and see what happens at depth. And it might be there are some levels and some instances where you have very prolific biosphere, and then suddenly it could be dead, and then suddenly it could spring to life again with the right conditions. What we've been seeing so far is an unexpectedly high amount of chemical fossils that are not quite fully chemical fossils yet, but then again they're not quite biological molecules. So the hope is that if there is a deep biosphere, it should, or it could leave a very sort of clear, distinctive chemical fingerprint that my colleague Yushi could detect.
I'm generally very interested in the big question of biodegradation. For human beings, we know that we eat apple, we eat hamburger, and this is very clear because we can see that. However, for microorganisms, it's very, very unclear what they are doing and if the organic matter is degradable for them. I'm also interested in knowing if the microbes, they are really degrading something. How do we know that? For example, when you see an apple and you found that there's some crack on it or some strange imprint from the teeth, then you know that somebody has eaten it, right? But how do we know that when we look at the rock, how do we know that the microbes, they have degraded the organic matter they are in? Yeah, so how do I use some molecular approach to see, okay, this is a biodegradation signal?
Just on the level of technology, for us it's not really the challenge to find life, it's more like to find life at this very, very low level in front of the background of all the fossil signals of life, because the sediment holds a lot of signals from past life over millions of years of fossil life, and that is where we see all the molecular signals, and we have to distinguish the few signals that represent actually current life from this large background. That's often a big challenge for us.
Hey,
What's the
Kai.
methane doing today?
Oh, it's doing very well. We have good recovery and get constant readings for the isotope values, and right now
Biogenic?
it's still biogenic, yes. It hasn't changed a lot since we went through the coal bed. During drilling, we measure the isotopic composition of methane that is coming up with the drilling mud from the borehole. And we do this in real time, 24 hours a day. And this information tells us immediately that the methane has a biogenic source. It's made by microorganisms, not by thermogenic processes.
I'm really happy about this profile, especially with how you can see how it extends the real measured values.
So we are now seeing here the gas coming up from 3,240 meters.
back into the 10 years ago, I had one of the mission as a starting subject. Please counter microbes on this sediment, and then we created the membrane for doing the cell counts on the microscope, and then I counted the fluorescence particles or the cell-like stuff. But the number was the 10 to the 10 cells or 10 to the 11 cells per cubic centimeter, which is the astonishingly high. So I suspect that it may be wrong. Finally, I found that the only 1% of that fluorescence guys were microbes. So meaning that the 99% of them were fake or wrong. Then that was the motivation to create the robot, to invent a robot to counter microbes. Without technology, no one can find the microbes in our 367 samples. So, meaning that someone can say that no microbes are in our sample, but we could find microbes since we have the good enough technology. So that's the very important and the interesting aspect of the science.
Using a computer-based approach, we can measure the very low biomass of microbial community in sediment at even 10 cells per cubic centimeter. This is a great improvement of cell count technology. We extracted DNA from core samples and drill mats under very clean condition. Then we studied the DNA sequence, and we can discriminate the indigenous microbial population to contaminants.
Jenny, how's it going here?
Ah, looks good.
Wow, just a huge methane peak and no other hydrocarbons. Looks like biogenic gas. What's the delta value?
Minus 68.
Minus 68. I think that's pretty much the same that we had on board. The sample is from 1 kilometer depth. It's exactly minus 68 per mil. Wonderful.
Some of the lipids that we look at have a very, very low concentration, and we really need to use the most advanced techniques that analytical chemistry can offer. We have one of these machines, and that enables us to go to very low concentrations in lipids and also very low concentrations of cells. And that's exactly what we need when we go down to the very, very deep samples in the deep biosphere.
I'm interested in looking at these unsaturated GGTs and these BDGTs and want to know whether they're present in both samples or only in the sediment.
In the water column, we would expect them here and here, but we don't see them. And when we look at the sediment sample, we see that there are additional spots, so additional lipids here and also here. So we can really see that these compounds are only found in the sediment.
Oh, wonderful. That's really promising. So they could be great biomarkers for subsea floor microbes.
Yes, and we have more samples, so we should really look into them to confirm this.
For working on the samples of Expedition 337, we really had to go beyond the state of the art.
We found that microbial communities in deep samples are similar to those typically seen in terrestrial soils or forest instead of marine sedimentary microbes. It was unexpected.
The sample is well prepared.
Can you please go to the two connected cells?
Okay. So go to 50,000 times magnification.
We can see the membrane structure.
Yes, it's great.
Very nice. So can you magnify it a little bit more?
Okay.
Very good. We can see clearly the membrane structure.
Yeah, exactly.
Also, we can observe the small ribosome-like structure as well.
Wonderful.
Very good.
We try to enrich the methanogenic communities in 2 km deep coal beds using a bioreactor technique. And after 1 month's operation of bioreactor, we saw some production of methane. Then when we pick up some coal particles and observe the particles under electron microscopy, we saw many cells were growing in the core particles. We are now keep cultivating the microbes and try to study more about the microbial community.
稲垣さんですか？
はい、
面白いのがちょっと見えてるんで、顕微鏡室までいいですか？はい、お願いします。
どうしたの？
これなんですけど、下北の 14R の1。This is from the 14R1, which is the 1800 meter below the seafloor, incubated with acetate for 6 months.
Oh, there are something, green ones.
Yes. Since it's from the sandy layer, we have to ensure the incorporation of the substrate with nanothings, but there's something.
It looks as if, it looks like dividing.
Yes, so there's a line here. そうですね。ここら辺分かれて、ここ切れ目が。
アクティベートされてるな。